Okay, good evening everyone. Today we'll be discussing problems on condensation and little bit some introduction to radiation. So last class we have done the boiling part and today we'll see some problems on condensation. So I'll be sharing my screen now. So the first question is this as shown in the screen. A 2 meter cross 2 meter vertical plate is exposed on one side to saturated steam at atmospheric pressure and on the other side to cooling water that maintains a plate temperature of 50 degrees Celsius. What is the rate of heat transfer to the coolant? What is the rate at which the steam condenses on the plate? So we need to find out the Q, rate of heat transfer, and what is the rate at which the steam condenses on the plate. That means this is the rate at which steam condenses on the plate is the m dot. That means Q by the latent heat. So uh, they have given the properties of the saturated vapor and the saturated liquid, and they have also given the formula already of finding out the Reynolds number. Okay, so first we'll start with this only, finding out the Reynolds number. So since they have already given, we will be calculating, we'll be computing this Reynolds number. So this is the formula given here, and here there is a term H dash Fg. That means this is the corrected latent heat. So first let us find out this H prime Fg, HFG prime. Then we'll insert this value here. So this HFG is equal to HFG. That means um, it's given here 2257 plus 0.68 CPL. So this is the specific heat capacity of the liquid 4193 into T set minus Tg. T set is the saturation temperature, which is 100 degrees Celsius, and then Tg is 50 degrees Celsius. So if we calculate this, how much we get? Okay, this thing we need to convert into this is kilojoule per kg, right? So we need to convert into joule. So 10 cube. So this is around 2399562. Since this is joule per kg, right? So we can write this in kilojoule also, but while calculating we'll be using the joule amount only. So if we write in kilojoule, we can round it off to maybe 2400 kilojoule per kg. Now we'll put this value in this equation. So we'll be writing the whole of Re now. Reynolds number. So Reynolds number is given by, I'm directly writing the values, 0.069 into KL is 0.668 into L. L is 2 meter, it's given, into T set minus TG, that is 100 minus 50, is whole divided by mu L. Mu L is given 375 into 10 to the power minus 6 Newton second per meter square into HFG. HFG we got as, we can directly write this also, or we can write this as 2.4 into 10 to the power 6. So 2.4 into 10 to the power 6 into mu square by G. So what will be this? 3.85 into 10 to the power minus 7 divided by G. G is 9 point, sorry. This divided by G, that is 9.8 whole to the power 1 by 3. Right. Now into, we have another numerator part, that is Prandtl number to the power 0.5. Prandtl number is given as 2.35 to the power 0.5. Now this plus, sorry, not plus, it's minus 151. Prandtl number is 2.35 to the power 0.5 plus 253 whole to the power 4 by 3. Alright. Now if we calculate the whole thing, we'll get this Reynolds number as 2370, and this is for film condensation. It is turbulent. Like if we see in the notes of which sir has taught, we can see here film condensation, this, if Re delta is less than 30, then it is in laminar, and if it is greater than 1800, that is 2370, whatever answer we got, that is more than 1800, so it is turbulent in nature. We see this. So this turbulent. The condense, then we can now find out what is the rate at which the steam condenses. So just now we saw the formula of Re from the notes. Re is equal to M divided by mu L into B. So we have this as 2370 into mu L is this 375 into 10 to the power minus 6 into B is 2 meter divided by 4. So we get this as 0.444 kg per second. So we already got what is the this part. No? What is the rate at which the steam condenses on the plate? We already calculated this. Now what is the rate of heat transfer to the coolant? So for this, this also requires this m dot q can also be found out from m dot into hfg. M dot is 0.444 into hfg. Also we have calculated 2.4 in this is simple. Okay, 2.4 into 10 to the power minus 6. Sorry, 6, right? So it is 1.66066 into 10 to the power 6 watt. So the answer is the first one. M is we get the rate at which steam rate as 0.44 kg per second and the heat rate as 1.066 or 65 into 10 to the power 6 watt. Okay, so we'll go to the next question. The next question is saturated ethylene glycol vapor at 1 atmosphere is exposed to a 300 millimeter high and 100 millimeter wide, having a uniform temperature of 420 Kelvin. So there is a vertical plate which is 300-meter high and 100-meter wide. Now there is here ethylene glycol vapor which is at this plate is having a uniform temperature of 420 Kelvin. Estimate the heat transfer rate to the plate and the condensation rate. Now ethylene glycol vapor properties are given. Now they have given a formula for Reynolds number, considering it to be a laminar flow. So for laminar flow they have given this formula for Reynolds number. Here also it contains this term, this corrected HFG. So again we calculate this. This is equal to HFG is given by 812 into 10 cube plus 0.68 into CPL is 2742 into T set minus TS 470 minus 420, that means 50. Alright, so what we get this as 8.9 into 10 to the power 6 or 8.97, you can write kilojoule per kg. Sorry, this is joule only. Once we get this, this is almost equal to 9 into 10 to the power 6. Okay, fine, you can also write it like that. Simplify it. Now we put this in this equation. So RE will be equal to 3.7 into KL. KL is how much? 0.263 into L. L is 0.3 into 50, right? T set minus TS is 50 divided by mu L is given by 0.215 into 10 to the power minus 2 into this 9 into 10 to the power 6 mu L square, that is 2.03 into 10 to the power minus 6 whole square divided by g is 9.8 to the power 1 by 3 plus 4.8, right? So whole to the power 0.82. Okay, so if we calculate this whole thing, we get RES. I'll write in the next page. So RE delta is given by how much it is coming? Around 45.4. That means it is clearly laminar. So whatever assumption was, it's correct. So after this, what they have asked to calculate, estimate the heat transfer rate to the plate and the condensation rate. Same thing again, Q and M dot we have to find out. So first we'll find out what is the condensation rate. RE is equal to that means M dot is equal to RE into mu L into B divided by 4. So RE was 45.4 into mu L. Mu L is 0.215 into 10 to the power minus 2 into B. B is the width, that means 100 millimeter. So it will be 0.1 meter divided by 4. Now what we get this as 0.244 into 10 to the power minus 3 or 2. 0.244 into 10 to the power minus 2 kg per second. This also you can also write as 2.44 into 10 to the power minus 3, since the options are given like this. So next you have to find out what is the heat rate, that is Q is given by m dot into hfg prime. M dot is 0.244 into 10 to the power minus 2 into hfg prime is 9 into 10 to the power 6. So it will be 2.19. So it should be 5, I guess, right? This should be 5. This should be 5. And this is the correct answer. So 2.19 kilowatt. Okay, this is the answer, final answer. So both the questions have been almost similar in terms of the concept. This one was in turbulent flow, another is in laminar flow. So we have seen two cases in condensation. Now we move to the next question. Now an uninsulated 25 millimeter diameter with a surface temperature of 15 degrees Celsius passes through a room having an air temperature of 37 degrees Celsius and relative humidity of 75 degrees. Estimate the condensation rate per unit length of the pipe, assuming film rather than dropwise condensation. So it is a film condensation. Again, they have given some formula for the heat transfer coefficient. So what they have asked to find, they have asked to find out the condensation rate. That means m dot per unit length. That means divided by L. Okay, per unit length of the pipe, assuming film. Now, how do we get this? M dot we get as Q divided by HFG prime, right? So Q is equal to HAS, HL pi dl into delta T or T set minus TS divided by HFG. Since it is M by L, so it should be Q prime divided by L. So just cancel it. So this is the formula, this is what you have to find out for this question. M dot per length. Or you can simply write in this notation also M dot prime. So first thing is we require this HL or HD, which they have already given the formula for. Okay. So HD for this again you need to find out this HFG prime. So we'll first find out that it's the same formula HFG plus 0.68 CPL into T set minus TS. So HFG is 426 into 10 cube plus 0.68 into Cp is 4180, right? 4180 into T set minus TS. T set is 333 and TS is, sorry, that was another question. So T set is, where is the T set? It's 300. This is the TS. Okay, sorry, this is the surface temperature, TS 15 degree. So TS anyways 37 minus 15, right? The temperature difference. No. Saturated temperature is given as this 305 Kelvin. So T set will be 305 and TS is 15 degree. So that will be 273 plus 15 is plus, right? 288. So it will be 288 Kelvin. Okay, so this is the surface temperature of the pipe, and this is the air at which the pipe is exposed to. But then they will condensate at this temperature only. That means it is the saturated temperature. So the T set is 305 minus 288. This whole will be equal to, if we calculate this, 2471 kilojoule per kg. You can also write as 2.4 into 10 power 3 joule per kg, right? So next is to find out the HD bar, which they have given us 0.729 into G rho L into rho L minus rho V, KL cube HF prime HFG prime divided by mu L T set minus TS into D whole power 1/4. So it is 0.729 into G is 9.8 into rho L. They must have given rho L 997.2 rho V they have given 0.04 into KL cube. KL is 0.609 to the power 3 HFG 2474, or you can write as this should be 6 actually. 2.47 into 10 to the power 6 divided by mu L. Mu L is 917 into 10 to the power minus 6. T set minus TS 305 minus 288 into B. Sorry, B is 25 millimeter, that means 0.025, right? If we calculate the whole thing, sorry, this not yet complete, this is to the power 1/4. Alright, now if you calculate the whole thing, you get HDS 7925 watt per meter square Kelvin. Now what we were about to calculate this, right? So M dot prime is equal to HD bar into pi d into T set minus Ts divided by HFG prime. So this is 7925 into 3.14 into 0.025 into 305 minus 288 whole divided by HFG is this 2.4 into 10 to the power 6. So we get this, if we calculate this, we get 4.28 into 10 to the power minus 3 kilojoule, sorry, kg per second meter. So m dot is kg per second, and if it is per unit length, kg per second meter. So we move on to the next question. Horizontal tube of 50 millimeter diameter, that means 0.05 meter, with a surface temperature of 34 degrees Celsius is exposed to steam at 0.2 bar. Estimate the condensation rate and heat transfer rate per unit length of the tube. Again, the same thing you have to find out. But here the condensation rate is also per unit length, m dot prime. Okay, and heat transfer also per unit length. Both you need to find out. So hint is given, it's a laminar film condensation. You have to assume it as a laminar film condensation on horizontal pipe, and it follows this. So HFG prime is equal to HFG plus 0.68 CPS T set minus TS. We can also write this as HFG 1 plus 0.68 if we write this as delta TE or delta T divided by HFGH. So this is given by, this is known as Jacob number. Okay. So anyways, we can directly find from here, or we can find from here also, anything. So HFG is equal to this 2358 into 10 cube is 0.68 into CPL is 4180 into T set minus TS. So TS is 34 degrees Celsius. If you convert into 273 plus 34, you get 7307. So 333 minus 307. How much you get this? If we calculate this, 2358 plus 0.68 into 4180 into 33 minus 7 is 26. Okay, so 2439, sorry, 2431902. That means 2.4 into 10 to the power 6 joule per kg. All right. Yes. Okay, so next we have to find out the HD bar, which is given by 0.729 G rho L minus rho V KL cube into H Fg prime divided by mu L Tset minus Ts into D 1 by 4. So 0.729 into 9.8 rho L is 989.1 into 989.1 minus 0.129 into KL cubed. KL is 0.640 into HFG. We have calculated as 2.4 into 10 power 6. Mu L is given as 577 into 10 to the power minus 6. P set was 333 minus 307 into diameter was 50 millimeters, so 0.05 meter. Right. So if we calculate this, we get HD bar to be around 6. This whole to the power 1 by 4. I have forgotten. So HD comes around 6926 watt per meter square Kelvin. Let's calculate. Since we are asked to find out both condensation rate and heat transfer rate, since we didn't calculate the Reynolds number, we'll first calculate this heat transfer rate per unit length. Okay. So this is Q prime is HD into per unit length is pi d into delta TE. So this can be written as 6926 into 3.14, 0.05. So this is 26. The temperature difference is 26, right? So if we calculate this, we will get the value as 28.3 kilowatt per meter. Six two nine six into 3.14 into 0.05 into 26. So it's 28,271 watt per meter. Okay, so we can directly write as 28 kilowatt per meter. Now next is to find out m dot. M dot we can find out with the help of this q prime. It's m dot prime. Okay, so q prime divided by hfg prime. So 28.3 into 10 cube, if you convert into watt, this is 2.4 into 10 to the power 6. So how much we get this? 1.167. So this is point 11.75 11.75 into 10 power minus 3. This is the answer. 1.17 into 10 to the power minus 2. Right? So next is the next question is saturated steam at a pressure of 0 0.1 bar is condensed over a square array of 10 cross 10 tubes, each of diameter 8 millimeter. So each one is having a diameter of 8 millimeter or 0.008 meter. If the tube surfaces are maintained at 27 degrees Celsius, estimate the condensation rate per unit tube length. So the outside, the tube surface, the TS is 27, and you need to find out condensation rate. That means m dot per unit length means m dot prime. This is asked to find out. Now the properties are given for saturated water vapor and water liquid. So what we start, just like the previous questions, we start with we can also assume by ourselves it is suppose if it is laminar, then we can consider that the same equation for HD, the heat transfer coefficient. So for that we need to first find out what is the HFG prime, which can be written as HFG 1 plus 0.68, just like, sorry, in the previous case I have shown this is 0.68 and this part is Jacob number. Okay, so 0.68 into GA. So this is just another form of writing this HFG. You can anyways calculate like the previous calculation. So if we calculate this Jacob number, this is equal to CPL into delta T by HFG, right? So if we calculate this, we get as CPL is 4178 into delta T. Delta T is, T set is given as 320 and this is 300 Kelvin. So 320 minus 300, this is equal to 300 Kelvin. And HFG is this 2390 into 10 power 3. Is 4179 into 20 whole divided by 2390. So this is 34.9 into 10 to the power minus 3, right? You can also write like this, okay? 10 to the power minus 3 means 0.0349, or directly you can write 35. HFG is again 2390 1 plus 2446.8 kilojoule per kg, or you can write 2.4 into 10 to the power 6. This is almost having a constant number. Okay, 2.4 into 10 to the power 6 joule per kg. Now we insert this in the formula of HD, which is given by 0.729 into G rho L minus rho V KL cube HF G prime. Now we have to divide, since it is an array of tubes, so it should be divided by n. Okay, n into mu L T set minus Ts into D. So 0. This whole to the power 1 by 4, obviously. So 0.729 into 9.8 into rho L is 993.1 into 993.1 minus rho V is 0.072. KL is 0.628 whole cube into 2.4 into 10 to the power 6, as we have calculated before. Then n is given in an array of 10 cross 10, so n is equal to 10. Mu L is 695 into 10 power minus 6 into 320 minus 300 into diameter is 8 millimeters, so 0.08. Now if we calculate this, we get the coefficient to be around 6210 watt per meter square Kelvin. So what we were asked to find out? M dot prime. So if we first calculate the Q prime. Okay, so this is HD into pi d into T set minus Ts. So 6210 into 3.14 into 0.008 into, so this is the difference is 20 T set minus Ts. We get this so the total Q will not be this. Total Q we have to calculate for all, for the whole array. So it should be multiplied with n. So into 10 we get here. So what we get this as 6210 Okay, so we get this around 31199.04. This is watt per meter. So we can calculate the m dot as m dot prime as q prime by hfg prime. So this is 31199.4 divided by 2.4 into 10 power minus, sorry, into 6, 10 power 6. We get this as 12999 into 10 to the power minus 6. So it should be so we need to calculate for the total number of tubes. So this is NT, which should be into 10 into 10 for this array. Alright, so this should be, if we multiply by 10, this should be like this. So we'll get it as 0.129 kg per second meter. But the uh, options are given in terms of hours. So we convert this into hour. 0.129 into 3600 kg per hour meter. It's coming to around 464. So it's almost uh, matching with the option B, 459. This is kg per hour into meter. Okay. So for the next question is just, it's not a numerical, it's just a small question. Consider the following statements regarding condensation heat transfer. So for condensation heat transfer, for a single tube, horizontal position is preferred over vertical position for better heat transfer. So for condensation, this statement is true. Horizontal position is always, because there the heat transfer is better. Okay, now heat transfer coefficient decrease if the vapor stream moves at a high velocity. So usually if the convection, if it is moving at a high velocity, the convection, it increases the heat transfer coefficient, the ability to transfer the heat, it increases. So this is wrong. It doesn't decrease it. Instead, the high velocity increases the heat transfer rate. The condensation of stream of an oily surface is dropwise. So this is also correct, because oil is hydrophobic in nature, so it will uh, prevent the film formation. So it will be mostly in dropwise. And condensation of pure benzene is always dropwise. This is wrong. So we get the correct statement as 1 and 3. Now we go to the next question. So this is a saturated steam at 1.5 bar condenses on the outer surface of a vertical 100 millimeter diameter pipe, 1 meter long, having a uniform surface temperature of 94 degrees Celsius. That means the surface temperature of the pipe is 94. Estimate the condensation rate, that is m dot. Here they have given the formula for HFG prime, though we can, after this, we can calculate the HD. If we're calculating that, first we calculate this Jacob number. Okay, this is equal to CPL is 4220 into Tsat. Tsat is 385 minus TS, that means 94, whole divided by HFG. HFG is 2225 into 10 cube. So it is again 0.034 because it is 34.114 into 10 to the power minus 3. Yes, we can write as 0.034. Alright, now we calculate this HFG prime. So HFG prime is equal to HFG is 2225 into 10 cube 1 plus 0.68 into 0.034. So 2276.4 into 10 cube, or we can write as 2.3 into 10 to the power 6 joule per kg. Okay, so we have to calculate the m dot. For that we require q, and q we get from heat transfer coefficient. And heat transfer coefficient, the formula for heat transfer coefficient is given. Okay, since we don't know it's turbulent or laminar, you can write this as from this you can see HL bar into UL square by G 4 to the power 1 by 3 divided by QL is equal to RE delta divided by 1.08 RE delta to the power 1.22 minus 5.2. Right now, instead of so we get rid of one of these terms, like if this HL, this can be written as HL bar is equal to into KL divided by UL square by G 4 to the power 1 by 3. HL bar is also equal to Q divided by pi DL into T sec delta T, right? So this is the left hand side actually, this one. So again, this Q can be written as m dot into HFG. So I'm writing the final equation, m dot into HFG divided by pi dl delta T is equal to RE 1.08 RE to the power 1 by 2 1.22 minus 5.2 into KL divided by U square by G to the power 1 by 3. Alright, so but you may not do all this also. From here itself you can find out HL, then M dot you can find out from this Q, Q thing. So from here we get this HL bar is equal to this, right? This one. Okay, but we don't know any of the variable. That is HL also we don't know, RE also we don't know, M dot also we don't know. So instead of M dot we can also write, or instead of RE we can also write this formula. Sorry, I have not been showing. So in this equations, this is the one which was written in the lecture, this one. Okay. So from here we don't know HL, we don't know RE. So instead of HL we can write Q by uh, A into delta T, right? This one. Now instead of Q we can again write M dot into HLG. This. Now again instead of M dot we can write RE equal into B divided by 4. Okay, so this will be all known terms. So this one we will put instead of this M. Okay. So now all the terms are known. This RE will be in this side and also in this side. Then you can calculate the what is the value of RE in this case. Okay. So if we substitute all the values of this, we get RE delta as 832. Okay. So this is actually in between laminar and turbulent. So once we get this RE, we can substitute here and here. Then we can get the value of HL prime. Okay, HL prime will be equal to, if we substitute all these values, we get this value as 7127 watt per meter square Kelvin. Now if you get the value of HL, we can write M dot S so from here we can also calculate Q. H into pi dl. What have they asked to find out? M dot only. Estimate the total condensation rate. Yes, only M dot. So Q is equal to pi dl T set minus T. If we substitute this L, H should be HL bar. So if we substitute the values, we get the value of Q as 40.3 kilowatt. Now this M dot should be Q divided by HFG prime. So 40.3 into 10 cube divided by HFG prime is given as 2.3 into 10 power 6. So you get this value as 18 into 10 to the power minus 3 kg per second. So this is the value of M dot. So we move on to the next question. Now a vertical plate of 500 millimeter high and 200 millimeter wide is used to be used to condense saturated steam at 1 atmosphere. At what surface temperature must the plate be maintained to achieve a condensation rate of? So this time they have given the condensation rate m dot. We need to substitute and back calculate and find out what is the Ts or T set. Ts, right? Surface temperature, Ts. So Ts we get from Q equal to HA T set minus Ts. Ts. Okay, so Ts is Q divided by HAS. T set minus this, right? So this should be minus, this should be plus T set. So T set minus this term. Okay. Now, the only thing is you need to find out this H. So for finding out H, again, the first term, refer question 1 for expressions of H, Fg prime and Jacob number. So Jacob number we find out first, that is CPL into so for initial consideration, they have given T as 74 degrees Celsius. Okay, so this is already given in question. So 74 means, anyways, this is given in Celsius, so we don't need to convert. So CPL is 4203 into 100 minus 74. T set is given as 100 and TS is given as 74 divided by HFG. HFG is 2257 into 10 cube. So calculate this as 4203 into 26 divided by 2257 into 10 power 3. So this is equal to 0. 200 minus 74 is equal to 26 into 4203 divided by 2257 into 10 cube. It's coming to be around 0.04. Then if we calculate the HFG prime now, HFG prime is equal to HFG into 1 plus 0.68 into 0.04. So we get this into HFG is 2257. So this is coming to be around 2331 kilojoule per kg, or we can write as 2.3 into 10 power 6 joule per kg. If you write in terms of kilojoule, then 2331. So I have just written directly in decimal 2.3 into 10 power 6 joule per kg. Now next is RM. We can RE. We can calculate. Divided by mu L is given how much is m dot 25 kg per hour. So we need to convert into hour in seconds. So 25 divided by 3600 all divided by mu L. Mu L is 324 10 power minus 6 into B is 200 millimeters, so 0.2. So this will be 100 divided by This is around 428. So this is again in between 30 and 1800, neither laminar nor turbulent. So we have to follow that formula. HL prime is equal to RE delta divided by 1.08 RE delta 1.22 minus 5.2 into KL divided by e to the power 1 by 3, right? So mu L is 324 divided by 967 is equal to 0.335 into 10 power minus 6. So this is the value of mu L. So if you substitute all the values, I think all other values are given. KL is also given. So we can find out if we calculate everything substituting all the values, we get this HL as 7312 watt per meter square Kelvin. Now from the first equation, this one, okay, so this Q is also given as m dot HFG. This is, so this divided by HLAS is equal to T set minus TS. So T set TS is also given as T set minus m dot HFG divided by HL into AS. T set was 100. This should be prime. area is 0.1 because it is uh, because it is 0.5 into 0.2, right? So it should be area is 0.5 into 0.2, that is 0.1. So again, if we calculate this whole thing, we get the temperature as 78 degrees Celsius. So this should be the answer. So if we go to the this answer is the second option. Yes. So we next move on. The next question is of radiation. We see here a small surface area A1, that is this is 10 to the power minus 3 meter square. So the area is given is known to emit diffusely. Okay, this side, and this side. From measurement, the total intensity associated with emission in the normal direction is IN is given as 7000 watt per meter square steradian. Radiation emitted from the surface is intercepted by three other surfaces of area A2, A3 and A4. Now all these are also having area of 10 to the power minus 3 meter square, which are 0.5 meter from the distance is given. Each are 0.5 meter from A1 and are oriented as shown. So these are the orientation. Now, what is the E radiation at surfaces A2, A3 and A4? So E radiation is given by this formula. G is equal to In cos theta 1 cos theta 2 E1 divided by R square. Now we just need to find out what are this uh, theta 1 and theta 2. Alright. The areas are anyways all 10 to the power minus 3. Okay. So for first we need to calculate this theta 1 and theta 2 individually for all the surface areas, that is A2, A3, A4. So for A2 first for A2 we see this theta 1 is this angle to this A1, that is this with the A2, right? So this is theta 1, this is 60 degree. Another is normal of this with the line connecting A1. So this is 30, given as 30. So here theta 2 will be 30. Okay, so if we write the irradiation, In is given as 7000 into cos theta, that is cos 60, into cos 30 into area is 10 to the power minus 3. R square means the distance 0.5 square. Okay. So what we get this so this and this all cancel out. Now the 7 will remain. 7 into cos 60 is 0.5. Cos 30 is 0.866. 0.5 square. This and this also we cancel. So this is around 12.124 watt per meter square. So this for area 2. So next we see for area surface area 3. Here it is the normal is exactly perpendicular this also this area. The normal to A1 is also the normal to A3. So theta 1 and theta 2 both are 0. So if we substitute the formula, we get I1 cos theta 1 cos theta 2 divided by R square. So this is 7000 cos 0 cos 0. Area is into 10 ms 3 divided by 0.5 square. So this is cos 0 is 1, cos 0 is 1. So 7 divided by 0.5 square. It's coming to around 28. For A4, if we calculate, theta 1 is 45. And if we draw the normal to this will also be 45. So theta 1 and theta 2 both are 45. Cos 45 is 0.707 square, 0.5 square. Okay, so the answer for this is not matching. Hmm. So I'll get back to this question in the next class again. The answer should be this because the first two are matching. But for the third one, we are not getting this. Okay, for this surface, what we see is we have to calculate the, theta 2 is for theta 1, it is first we need to see the surface of the first surface, that is this A1, and the normal to this A1, that is this line. And the other line is made by, suppose if we take A3, then we have to take the normal of that. Okay, for theta 1, uh, the angle made by the normal to A1 with the connecting line between the other surface, so maybe A3, A2, A4, that is theta 1. Okay, that is normal to A1 and line connecting with any surface. So that is theta 1. And for theta 2 is just the opposite. The normal to the surface with the line connecting with A1. So for A4, what we get, just like in A2, we have seen that this is the A2. For A2, the theta 2 is measured by the normal to this surface is this with the line connecting the A2 with A1. Okay. Same way for A4, what we get is the theta 2 is the normal connecting this theta 2. For A4, this is already tilted, so the normal is already this line. The normal and the line connecting the A4 to A1 is the same, so the theta 2 is 0 here. So I've made a mistake here. Because 0 is 1, so now we get as 19.8. So this is the correct answer. So we have to be very careful with how these surfaces are oriented and how they are connecting. How they are receiving. We need to exactly find out the angle made between these surfaces. Okay, how they're receiving the, how A1 is emitting the radiation, or how other surfaces are receiving the emission from A1. So next is according to its directional distribution, solar radiation incident on Earth's surface may be divided into components. The direct component consists of parallel rays incident at a fixed zenith angle theta, while the diffuse component consists of radiation that may be approximated as being diffusely distributed with theta. Now we just need to find out what is the okay. Consider clear sky conditions for which the direct radiation is incident at theta is equal to 30 degree. So the zenith angle, this theta is made by, so the zenith is this point exactly. If this is the Earth's surface, then the zenith is exactly calculated from the normal to the Earth's surface. That is this, with respect to this, the zenith angle is calculated. I mean, if the sun is present here, then they have given us theta is angle of incidence is 30 degree. So theta is equal to 30 degree. With a total flux, this is centigrade, this is not centigrade, this is the degree. With a total flux based on an area that is normal to the rays of uh, Q diffuse is equal to 1000 watt per meter square, and the total intensity of diffuse radiation is this. The intensity is given. What is the total solar irradiation at the Earth's surface? So total irradiation is given by, if we see the total is direct plus diffuse. Okay, so direct is given by, direct is the one which is directly falling, that is parallel, this one. So this angle is 30. The sun is present here. This angle is 30. So these are the direct rays, and the other rays are diffuse. The ones which are parallel, those are direct rays that are directly falling on Earth, and the other uh, which are made at different angles, those are diffuse rays. So G total irradiation total is given by G direct plus G diffuse. So G direct is given as Q direct into cos theta plus G diffuse is pi I diffuse. Okay, so Q direct is cos theta. Cos 30 is 0.866 plus 3.14 into, this should be actually direct, Q direct. So it is already given for which the direct radiation is incident with a total flux based on an area that is normal to the rays. So this is calculated from the normal to the rays. So this is Q direct is given. This should be DIR, not DIF. So if we substitute the values 1000 into 0.866, this is for cos 30, right? Theta is 30 degree. Now pi into I diffuse. So I diffuse is given as 70. So if we calculate this, we get this around So it is 1085.8. So almost equal to this 1086 watt per meter square this time. Okay. So next we on an overcast day, the directional distribution of the solar radiation incident on the Earth's surface may be approximated by an expression of the form I is equal to In cos theta, where In is equal to 80 watt per meter square steradian is the total intensity of radiation directed normal to the surface, and theta is the zenith angle. What is the solar irradiation at Earth's surface? So if you calculate the total irradiation, cos theta sin theta d phi d lambda. Now I is given as In cos theta. So this lambda, this can be written as 0 to 2 pi, 0 to pi by 2. Instead of this is I. This can be written as In cos theta. Sorry, here there is theta. Again cos theta sin theta d phi. Now this d phi, if we integrate from 0 to 2 pi, we get 2 pi, and this comes out. So 0 to pi by 2 cos square theta sin theta d theta. Now if we integrate this, we get as minus 1 by 3 cos cube theta 0 to pi by 2. Now if we substitute 0 to pi by 2 in cos theta, we get this g as and we also substitute the value of in as 80. Okay, we get this as 1.67 into 60 watt per meter square. So if you write this, cos 0 is 0, cos 0 is 1 by 3 minus cos pi by 2 is 0, so it will be anyway 0. So we should get so it's coming 167.466. Okay, so this is the correct answer. Okay, the next question is the spectral distribution of radiation emitted by a diffuse surface may be approximated as follows. What is the total intensity of the radiation emitted in the normal direction and at an angle of 30 degrees from the normal? Okay, I don't know why they're giving C everywhere. So this total intensity is given by this total intensity of the radiation emitted, E lambda to lambda d lambda. So this is E lambda is given as a y-axis and lambda is the x-axis. So the integration of this is simply the area of this curve, by this graph. So from 5 to 10 is 5 into what is the value of E lambda there? 100 plus from 10 to 15 is 200 plus 5 to 20 is 5 into 100, again 100, right? So 500 plus 1000 plus 500. So this is 2000 watt per meter square. So this is the total radiation. Now if you want to find out the intensity we can just like we have found out this divided by pi. So total E divided by pi, 2000 divided by pi. So we get it as 637 watt per meter square steradian. So this will be the answer. Okay. So for we stop for today. Let's start with the next topics on the next class. So we'll continue in the next class. Thank you.